So if we're looking at one period of the tangent curve, we need to remember a few things. Now, one of the quiz trade cards floating around had this on there, and if you had that quiz trade card, tangent of theta can be described as what over what? Sine over cosine. Okay, that's important because we're going to take the values that we've gotten for sine and cosine for these different things, and we're going to put them in the table. Okay, if you have your unit circle out, I forgot to say that at the beginning of class, but if you have your unit circle, that would be helpful because you'll see where I'm getting the values from in my head. I'll give you a second to find it. So one more thing to remember, and we went over this again when we did sine and cosine the first time, but it's been a minute. Remember, all of these coordinates around your unit circle are cosine, comma, sine. Okay, so at 0, find 0 on your unit circle. We want the ratio of sine to cosine for tangent. So what is sine at 0? 0. What is cosine at 0? 1. So 0 over 1, that's just 0. Okay? Go to pi over 4 on your unit circle. What is sine? Square root of 2 over 2. And what is cosine? So you have square root of 2 over 2 over square root of 2 over 2, which is 1. Okay? I guess I should put equals 0 here. All right, then we go to pi over 2. We're doing sine over cosine. So what is sine?
0.
Remember, sine is the second coordinate. 1. And then what is cosine? 0. Ooh, yuck. I have 1 divided by 0. What does that mean? That means that this is undefined. And what's going to show up on this graph?
Asymptote.
A vertical asymptote. Let's go to 3 pi over 4. So that's in the second quadrant. Sine divided by cosine. Yeah, we have square root of 2 over 2 over negative square root of 2 over 2, which reduces to negative 1. Okay, we go to pi. Sine over cosine. Sine would be 0. Cosine is, but 0 divided by negative 1 is still 0. There's no such thing as negative 0. 0 is not neither positive or negative. It exists. It's just neither positive or negative. If we start to notice this pattern, because at this point we've thought a lot, look at the pattern we have here. We had 0, then 1, then negative 1, then 0. Oh, sorry, I missed a vertical asymptote. 0, 1, vertical asymptote, negative 1, 0. What do you think is coming next? Ooh, not yet. 1, and then vertical asymptote because it's undefined, and then negative 1, and then 0. Ooh, so tangent still has a pattern the way the other graphs had a pattern. But when we graph that, it's going to look a little bit different. Here, we're starting at 0, and I'm just doing the positive side because that's all we have on our table. We have 0, and then 1, and then a vertical asymptote. And then the next one is negative 1, then 0, then 1, and then a vertical asymptote. And then negative 1 and 0, the pattern would complete. But remember, this is, I don't know where I was going with that sentence. So sorry. If we're playing connect the dots here, try not to make them straight lines. They are not straight lines. They are still curves. So it's going to curve and then jump down and curve and then jump down and curve. So here's why our calculator looked crazy whenever we graphed tangent in it just a second ago. Because we have vertical asymptotes, we have zeros, but they're not in the repetitive pattern that we had in the other one. It's a different pattern. If we were to follow this the other way, all I'm interested in truly is the vertical asymptotes and the centers. The 1 and -1 is extra information. So we know that this is a center. And if I skip 2 of them, my vertical asymptotes are appearing at multiples of pi over 2. And then I have a center. And then I'd have another vertical asymptote. And then I'd have another center. Again, I know we could add more information about where 1 is, but I don't need it as much as I need you to get the shapes and the periods correct. That's what tangent looks like. It's wild. Here's what's also weird about it. For sine, cosine, sine, cosine, secant, and cosecant, the period was always 2 pi. What's the period on this one? How long does it take for my graph to start repeating itself? Just pi. So tangent has a shorter period than the other ones. Interesting. This one, you can't even pretend it's an amplitude, but its vertical stretch is 1. That has to do with this number. So if yours is vertically stretched up, that just means that the extra information would be further, so it's going to be a steeper tangent curve. We don't call it, again, we don't call it an amplitude anymore because it's truly not an amplitude here. It's just a vertical stretch number. The domain, is it going to be all real numbers? Yeah, what are all these dashed lines I got drawn here? That's tough. Are those numbers in my domain? No, because they're vertical asymptotes. So when we talk about the domain, we have to take them out. So we would say the domain is all real numbers except the places that we have vertical asymptotes. So where did the first vertical asymptote appear? And how long did it take until I got to the next one? Pi. So we would say the domain is all real numbers except pi over 2 plus pi times k. Now when we talk about range is very interesting for this graph because you feel like it's got to have some breaking points in it because there's all these breaks for the domain. But remember, range is talking about the lowest number it can get to and the highest number it can get to. What's the lowest number this can get to?
-1 infinity.
What? Negative infinity, and the highest it can get to is?
Pi infinity.
So all real numbers for the range, which is interesting, considering the domain is so restricted. The equation for the vertical asymptotes, we've technically already found because we used it in our domain. It's x equal to pi over 2 plus pi k, which is the first vertical asymptote I see, and then the distance from the first to the second. But for this one, we can also make an equation for the general solution, or the zeros. Where's the first 0 that you see? Even before that. 0. Well, there's no such thing as negative 0. No such thing as negative 0, but okay. And what is the distance from the first 0 to the second? Pi. So 0 plus pi k is the general solution for all of the zeros for this entire tangent function. Ooh, and then symmetry. Our two options for symmetry are that it's even or odd. Even means I can fold it along the y-axis. Can I do that?
No.
No. Can I rotate it around, putting a pin in the origin?
No. Yes.
Well, let's think about it. So here's the pin in the origin. Even just look at this 1 in the center. And if you rotate this one, does it land back on top of itself? I mean, if I drew it better, yes. The way I drew it, it didn't. But this is actually an odd function. It is symmetrical about the origin. It goes through the origin, and it's not reflective over the y-axis. And now here's the important stuff to help us figure out our pattern. Comparing tangent to sine and cosine. So thinking about sine for a second, the shape of sine, you had center, max, center, min, center. And if you think about cosine, it was max, center, min, center, max, okay? Comparing those shapes to this one. Tangent has a vertical asymptote at the zeros of blank. So which one of the functions that we learned about in the last couple weeks has zeros here and here? So if we follow sine, it goes center, max, center, min. That's too close. Sorry. Center, max, center, min, center. So at this point, are we at a center?
Oh, yeah.
Center, max.
No.
No. Okay, if we go to cosine, it's max, center, min, center. So the zeros of cosine are the vertical asymptotes of tangent, which you can probably figure out what happens next. The tangent function has zeros at the zeros of sine. Bless you. So if you were to graph all of them at the same time, every time sine crosses, bless you, the center line, your tangent would cross the center line. Now what this means for us is when we get to our pattern, the sine pattern is center, max, center, min. And the cosine pattern is max, center, min, center. Bless you. The reason I'm having you write those down is because remember, tangent is the combination of the two. Even more so, we now know what's happening at the zeros of both cosine and sine. So if we were to write down the pattern for tangent, every time you say center for one of the graphs, something interesting will happen for tangent. For sine, everywhere there was a center, what did we say was going to happen for tangent?
Zero.
A zero, so that's the centers. At the centers for cosine, what's going to happen at tangent? A vertical asymptote. That is the x increment pattern that you're going to be using for tangent. Center, vertical asymptote. Center, vertical asymptote. Center, vertical asymptote. Over and over again. So when you have to graph it, you follow the same rules that we always did, finding the b value to figure out the period, and then the x increment, and on and on. Yes? That's tangent. Kind of a mess. And then we get to cotangent. The reciprocal of that one. Woo! Okay, I've already filled in the table for you. And if you remember, bless you, like we did for secant and cosecant, we're just going to do the reciprocals of the values in the table. So at 0, tangent is 0, which means cotangent is what? Undefined, which means there will be a vertical asymptote right there. At pi over 4, tangent is 1. So cotangent is 1. The reciprocal of 1 is still 1. Okay? Then at pi over 2, tangent is undefined, which means cotangent would be 0. The reciprocal of undefined is 0. At 3 pi over 4, tangent is -1, so cotangent would be -1. And then we get to a 0, so that would be undefined, so a vertical asymptote. The reciprocal of 1 is 1. The reciprocal of undefined is 0. The reciprocal of -1 is -1. And the reciprocal of 0 is undefined. Another vertical asymptote. Okay. Let's graph the positive versions of this one. This time it doesn't start off at 0. What does it start off with? Undefined. So we have a vertical asymptote at 0. At pi over 4, we have 1. At pi over 2, we have 0. At 3 pi over 4, we have -1. And at pi, we have undefined. And then +1, 0, -1, undefined. So here's cotangent. Again, they're not quite straight lines. Try not to make them super straight between those points, but when you start stretching this graph out, it's almost impossible not to. So if we continue this pattern just the other way, again, I really only care about the centers and the vertical asymptotes. The 1 and -1 I don't necessarily care about because we're just making good sketches. So the next time I'd have a 0 is at -pi/2. The next time I'd have a vertical asymptote is at -pi. And then -3pi/2 with the center, and -2pi with a vertical asymptote.
Who's on the back?
Mm-hmm. And that's cotangent. Also kind of a mess, in my opinion. By the way, at the top of your notes, it says the wrong title. Mine says the correct one if you want to change it. I think it still says 1 period of the secant function, but this is cotangent. My bad.
Will any of these equation would they ever have for something?
Okay, what is the period of cotangent? How long does it take for it to repeat? Still pi, which makes sense since it's the reciprocal of tangent. It has to be related to the tangent stuff. Its vertical stretch is 1, which again refers to this distance. So if you've stretched it out, then the in-between points are just higher, or if you shrink it down, then they're just lower. But there's no amplitude to this. The domain would be all real numbers except all of the places where there are vertical asymptotes. So where's the first time you see a vertical asymptote? 0. And then how far away is the next one? Pi. This one's range is, again, all real numbers because those arrows go off to infinity and -infinity. Okay, cool. So knowing that our domain is all real numbers except where there are vertical asymptotes, we already found the equation for vertical asymptotes. It's going to be at x equal to 0 plus pi k. That's where all of the vertical asymptotes appear. And if we write an equation for where all of the zeros appear, where's the first 0? Pi/2. And what's the distance to the next one? Pi again. So pi/2 plus pi k. Okay, again, our options for symmetry are even and odd. Can we fold this one along the y-axis and let it land right on top of itself? No. Can we put a pin in the origin and rotate it around? So remember, we're putting a pin right here, and we're rotating. And I can't rotate on here. Rotating like this? Yeah, it ends up landing right on top of itself. So it is, again, an odd function. One last typo for you. Even I didn't catch this one when I made my version. That should say cotangent. So if we compare cotangent to sine and cosine so we can get a pattern, looking at the graph and thinking about what the shape of sine and cosine look like, cotangent is going to have its vertical asymptotes at the zeros of which function? So which function has zeros at 0 and pi and 2 pi? Sine. So cotangent has vertical asymptotes at the zeros of sine. It also has zeros at the zeros of cosine. And what that means for us is that our pattern for x increment when we try to graph this is going to be related to sine and cosine. So we're going to write those down again just because it's nice to see them. And if we get to cotangent, we just remember that the centers of sine will create vertical asymptotes, and the centers, bless you, of cosine will create centers or zeros. So anywhere I see center on sine, vertical asymptote. And anywhere I see center on cosine, what's happening? It's a center, a 0, if it's on the x-axis, or y-axis. No, x-axis. Oh my gosh. So our pattern for cotangent is vertical asymptote, center, vertical asymptote, center. What? Okay. And again, everything else kind of stays the same with the letters that we've been using for the different types of stretches, shrinks, phase shifts, affecting the period, affecting the displacement. All of that is still the same. So if your displacement is like +5, then your center is just up at 5. The whole graph shifts up. So all of those rules still apply that we've been using. Yes? Okay.